My name is Baud Rate. I wanted to tell you a little bit. Can't hear me? Testing. I'll grab one of those. Yeah.
Should be long.
Is that better? All right. Thank you for coming. My name is Baud Rate. I wanted to tell you a little bit about some of the experiments that I've done over the past year with software-defined radio, just so you get a bit of a flavor of some of the cool things you can do. I'm the applications specialist / SDR evangelist at Edis Research, and luckily I get to have a bit of fun with the product. So this is a little journey I went on earlier this year. I really love SDR, showing people the cool things you can do with it. This was in Europe, and this was a lab that I took part in teaching this group of people from developing nations about SDR. And usually when I travel, I also have the good fortune of teaching the local constabulary about SDR as well. They always seem to show up at exactly the right time. But today, I'd like to quickly show you things that you can do with the restaurant pages, the traffic message channel on RDS, the radio data service, looking at primary surveillance radar, and some RFID applications. And pretty much everything I've done is using GNU Radio, which I'm sure you've heard about. It's a really neat open source DSP/SDR framework, and it's got a very vibrant community behind it. So over the past few years, there's been an explosion in bandwidth that you can actually achieve to peripherals that you plug into your computer. So this is, for example, 50 megahertz worth of spectrum being captured in real time going through another piece of software I love to use called Baud Line. And does anybody know what band we're looking at here? Any guesses? One guess? Come on, anyone? It's actually the cellular band. So right in the middle here, you've got some GSM channels and some wider bandwidth channels. Actually, the title slide here is a portion of that. And what's really cool about this program is that you can run the FFT so fast, you can see the frequency correction burst in the control channel coming down on GSM. And that's what your handset uses to synchronize its internal oscillator. And then this is actually a video of it running, I think, maybe, there we go. No, my laptop just needs a moment. There we go. So this is actually it scrolling past. You have some traffic, GSM traffic there on the left-hand side, and on the right-hand side you can see the control channel. And at this kind of resolution and transform size, you can see the symmetry that's due to the GMSK modulation that's used for 2G GSM. And this video here is actually the 400 megahertz band. I think this was 100 megasamples per second, so this is 100 megahertz worth of bandwidth. This is going over a 10 gig pipe from a sort of higher end USRP. The USRP that I used, just before I get to that, if graphics doesn't quite do it for you, you want to kick it old school, with some ASCII art, you can have an ASCII art FFT. You know, you might want to SSH into a remote console or something. You don't want to do X11 forwarding. You can just pop open one of these. This is actually 200 megahertz worth of bandwidth centered on the middle of the FM broadcast band. So you know, you can stream an incredible number of hertz essentially into your machine. So what I've used for my experiments is pretty much this: the USRP B200. You can pass it around if you want to have a look. It's USB 3.0 bus powered. You can get up to 56 megahertz of RF bandwidth over USB 3. It tunes from 70 megahertz to 6 gigahertz. The B210 can do 2x2 MIMO, so you can have full duplex 2 channels. And you can do all sorts of incredible stuff with this, like I've run an LTE base station off it. But anyway, the first thing, restaurant pages. Whenever I have these title slides, the actual FFT there is related to the signal that's being analyzed. So I'm sure you know what these pages look like. You go into the restaurant, you order your food, you're given one. They beep when your order is ready, assuming it's in fact ready. And if you consider the rate at which orders come into the restaurant and then the rate at which food is picked up, it should be roughly the same. But it's possible to tip that balance slightly. For example, if everybody might be paged at once. So if you want to figure out the frequency, you can either look at the frequency, which is sometimes on the device. You can look at the FCC ID and look it up on the database. Tells you what the licensed frequencies are there. Or you can actually just use an SDR like a spectrum analyzer and find the strong signal. So this is an example here. This is using HDSDR. There's the page. I have some audio here. Let's see if we can hear what it sounds like. Did you hear that? Bring some more volume. Okay, so that's some custom pager protocol, and if you actually look at the FFT at a higher resolution, you can see the two different frequencies that are used in this frequency shift keyed modulation. So one frequency will be a 1, the other frequency will be a 0. And the interesting thing about this plot here is that there's no long run of 1 or 0s, which pretty much gives you a clue about the line encoding used for this modulation. So once you actually construct this sort of flow graph in GNU Radio, you can demodulate that and then extract the raw bits and then process those to figure out what protocol is actually in use. So this is the first step. You need to record your channel and then identify the signal of interest. And then you move that down to baseband to center it on the dial. And you can use that with one of these blocks. Once you actually have that moved to 0 to DC, then you need to figure out what the deviation is for your frequency shift keying, which is finding the frequency range from the left-hand peak to the right-hand peak. So that might be a 0 here, 0 to 1, and you need to figure out what that range is. Once you've figured out that range, you can then put it through the Quadrature Demodulator with the appropriate gain, and that will scale your signal along this time series to be between 1 and -1, which is kind of normalized units for your incoming stream. After that, you need to figure out how quickly your bits are coming in. So this is your baud rate. And you can do this with a simple construction in GNU Radio. This is using this thing called cyclostationary analysis. And you basically multiply the original signal by a delayed version of itself and then take the FFT. It's a little bit of a trick, but it's cool because it actually shows you the periodicity of the incoming bit stream. And here you look at the first peak, and then you can just simply read off what the baud rate is of your incoming bit stream. And once you've got all this information, then you can do clock recovery, which actually means that you take in your raw samples and then you slice and you extract a 1 or a 0. If it's above 0, you treat it as a 1. If it's below 0, then you treat it as a 0. And then you have your raw bit stream. And this is what it looks like coming out. So you see some sort of repeating preamble here, and then you have some sort of a payload after that. And presumably in there it's encoded what pages should go off. So, you know, we always say, oh, you know, flow graphs are easy, just throw a couple of blocks together and you're all sweet. I told a bit of a fib in the previous one. I hid all of the disabled blocks. So the disabled blocks are in gray, and I produced all of those plots by sort of adding these graphical sinks along the way to probe the signal. But this is more a complete picture. I get a lot of crap about my flow graphs, but anyway. So those blocks that I was telling you about there, you've got the frequency translation, Quadrature Demod, clock recovery, figuring out what the baud rate is. And so once you've got your raw bit stream, these are the raw bits. So this is a little program I wrote a while ago to look at a different system, but you can import raw bits and then play around with different combinations of, you know, line encoding, character encoding, start bits, stop bits, and so on to try and tease out some sort of information from these raw bits. So here you can see again you've got no long strings of 1s and 0s, they're alternating pretty quickly, and that gives you a good clue that they're probably using Manchester encoding. So when you turn on Manchester encoding, it halves the number of bits because what happens is it treats your information in pairs. So like a 0 and a 1 will be treated as a 0. A 1 and a 0 will be treated as a 1. It's just a way of enabling better clock recovery so you have more transitions in your data for the receiver to synchronize. Once you do that, it starts looking more like a proper packet. And you can verify that it is in fact Manchester encoded by moving the bit offset. So let's say you forget the first bit in this unencoded view, and then once you move the bits, you get line encoding violations, and they're highlighted in red. And that's basically because with Manchester you can't have a 0-0 or a 1-1 in the raw input stream because you need to have a transition through the middle there. So that's just good verification there. Once you actually capture multiple pager transmissions, then you can put them side by side and highlight the differing bits to sort of figure out where the ID might be encoded. So you can see there are some bits changing here and at the end there. And now, once you actually get a pager, you check the ID, and then you look in your Manchester decoded stream and think, oh, hang on, what do you know? There it is. There's also this odd byte at the end that was changing, as you saw before. That's the checksum. And you can go through and try a whole bunch of different CRCs, algorithms. Turned out it wasn't actually CRC, it was really simple. Excuse me, you add up your bytes and you mod 255. It's a very simple check, and so that matches, as you can see there. So that's pretty much the packet format. And to do in the modulator, you just do the reverse. So you construct your packet, add your preamble, your magic header, the pager number, the checksum. You interpolate that to start producing the stream that will be sent out of your radio. You frequency modulate. Before that, you should actually do some pulse shaping. I didn't bother. And then you resample so that you can send it directly to the transmitter. So this is actually the transmitter, the modulator, and you've got the steps that I just talked about there. Goes out of the USRP at the end. And when you look at it on the FFT, again, it looks very similar to what we captured off the air from the original system. So you get something like this. Put the number in. That's the GNU radio program. And there you go. So that's system number one. I actually had a bit of fun. My colleagues and I went out for lunch to this place, and I took my laptop and my USRP, and I was just saying, oh, look, just ignore me. I'm going to be capturing a little bit more data to try and figure out what's going on. But in actual fact, it was all working. And I looked at my boss's pager ID, and then I set up this Wi-Fi tethering from my phone to my laptop, so I would have an XML server running on my laptop. And then I would have this web interface on my telephone. And so I could actually just type the numbers in on my telephone away from the table and set them off. So I just said, oh, I was going to the bathroom or whatever. And then I typed in his number, and his thing went off, and then he went to get his order, and then lots of chaos ensued when he tried to claim his order at the kitchen. But he liked the troll. I think he enjoyed that. So there's another pager system. This actually uses more of a standard, it's an established standard, POCSAG, which is used for normal pages, as you might recall. You can actually decode pages already with a nice out-of-tree module for GNU radio called GR POCSAG. I took that and modified it a little bit for this one, and this is the flow graph there, but this is just your POCSAG decoder block right in there. And if you look at that on the scope, you can see your preamble again, your payload, and actually the decoded frames coming out on the left-hand side. Now, the decoded frames have this odd structure for this system where you have a bunch of differing number of idles and then some sort of an address and data payload after that. Let's look at one in particular. So initially you have a sink, so the receiver can lock. You have a varying number of idles, you have an address field, and then some sort of data payload, and then another padding idle at the end. So what's going on here is with POCSAG, in this system, the zeros are just padding. I think the next 4 hexadecimal digits here are actually the system ID of the pager system at that particular restaurant. And then the last byte here is actually encoding the pager address. But for POCSAG, the way it works is, for the address, you take the last 3 bits, you multiply them by 2, and that's what gives you the index into this slotted structure that you transmit. So as you can see here, this is 3, you multiply it by 2, you can get 6. And the reason why they do this is back in the day when everybody had the beepers, to save battery power, the radio's receiver would only wake up in the slot where it might expect its address to be. So if you consider that you're going to send a page to a particular beeper, you're going to send it to an address, it knows what its own address is, and it knows what slot it can expect it to be in. So the radio will stay off after the sync in all of the other slots, where it would never be addressed, because they would be for somebody else. And then it would wake up in the slot, check. If it's there, then it receives everything. If it's not, then it goes back to sleep. And that can save you a huge amount of battery power. So to construct that again, you have your preamble, you have your sync, you have the system and a pager address, you put in the right slot, you pad it with idles, and then you need to apply this forward error correction, which is this BCH code that the standard uses. And if you do that, went out with my colleagues again, so we had a bunch of pages to play with, And you can kind of...
39, and then we'll do 56, and we'll do 83, and then 82.
Anyway, you get the idea. And then the final system was a ZigBee one, and this is pretty cool because it actually reverses the roles. So in this case, the pages transmit back to the restaurant where you've actually sat down. So on the tables, underneath the tables, they have RFID chips, and this has an integrated reader that will read out the ID of the table that you're sitting at. And then when your order is ready, they come and deliver it to you, but they know where you're sitting. And it uses ZigBee, and so it operates in the 2.4 gig ISM band. And you can actually decode this with GR IEEE 802.15.4, which is a really elegant implementation of the entire stack and a transceiver as well. So this is what the flow graph looks like there. You've got your USRP source coming in, you've got your PHY implemented Mac and another app stack on top of that, and it just goes out to your sync if you want to have a full transceiver. But in this case, that was a little setup, just recording there when the pages would be placed on the table. You can see that there's an obvious transmission happening there and the packets coming out on the left-hand side. If you drop this into Wireshark, then you can see decoded ZigBee data there. If you look and remember the 2 page numbers we had, turn them into hex. What do you know? They're in the payload. I actually went then to the kitchen and looked at their screen and figured out what table number we were sitting at. Happened to be 36. Turned it to hex. That's in the payload too. There you go. All right. Now, if you want to take a page hostage for whatever reason, then usually when you take it out of range of the system, it can't hear the beacon anymore. And so it'll get angry and light up and make lots of noise. If you wanted to take one hostage, then you could, I guess, simulate your own beacon, and then it wouldn't get angry for, whatever reason, why ever you would want to do that. So that's pages. Any questions so far? Any comments, or just feel free to shout out whenever you want. The next thing I looked at was cracking the encryption on the traffic message channel that's used in RDS. The background here is actually a large portion of the FM broadcast band, so you can see the various radio stations there. What's really neat is if you zoom right in, you can actually see over a very short space of time how the carrier is actually modulated by the audio that's being broadcast by that station. So I think here, for example, somebody's actually talking. This is a bit of speech here. See, these are moving much more, so there's probably a lot more modulation going on, but this is someone's speech. And if you also look closer, you can see modulator on there, the 19 kilohertz pilot tone, which is used to recreate stereo audio and so on. This is a sort of wider view, but if you look at it in a video, you can see that kind of modulation taking place there. It's kind of a good idea, a good way to get an idea of how a signal works. So with RDS, you've probably seen on your radio receiver, it'll actually tell you like the station name and the name of the song and so on. And it's a sub-carrier on commercial FM stations. It's not audible because it's filtered out. It's BPSK and it runs at this odd baud rate. You can listen and decode with this out-of-tree module called GRRDS. And this is an example here. This is Sutro Tower in San Francisco. They broadcast a whole bunch of FM radio stations out of that. And if you, for example, hook up a B200, then you can run the program, and this is what you get on the screen. This is the baseband. I'm listening to a particular station here. You can see the RDS traffic scrolling up on the left-hand side. It decodes that and then forms this sort of text panel down the bottom, so you get the station name and the program name and so on. And this is actually once you look at the demodulated portion of the signal. So this big peak here is the 19 kilohertz pilot tone. To the left-hand side of that is your mono, left plus right. To the right-hand side of this is your stereo difference channel, so that's left minus right, and then your receiver will combine the two to recreate your independent left and right channel, so you get stereo audio again. Beyond that, you actually have your RDS subcarrier up here, which is on the... you basically multiply this pilot tone up to center in on that subcarrier. So what we want to do then is look at the traffic message channel, and this is a compact representation of events, traffic events in your area. So you basically have what events it is, where it is, how long it might last, and some examples are, traffic congestion, when accidents happen, or when there's road work, for example. And here's an example. This is the nav system in my car. You have these congestion icons that pop up, and you have these are road work, and then you have the highway congestion along there. Now, the thing is, I thought, that's cool. you know, it'd be nice to receive this and make your own map, because I like making maps and visualizing things. This is an example of what you see as it's received. So, you know, congestion, average speed, sunny periods, and things like this. Basically, you know, this isn't particularly helpful, but the problem is that the location codes are actually encrypted. Elsewhere in the world, they're not encrypted. In America, they are. Now, apart from receiving, with GRIDS, you can transmit. Obviously, you know, this is in my car, and it's coming from somewhere else. As it happens, just a B200 there on my laptop. I'm making my own little FM radio station. As you might recall, that plot we saw before, this is the same plot, but with no noise, because we're actually synthesizing we're synthesizing the signal. So here you've got your mono, your pilot, your stereo difference, and the RDS. And this is actually then being received by the car radio. So the location codes are 16-bit for a geographical area. The encryption keys are 16 bits. And every day they pick one of 31 keys, which are already pre-programmed in the receiver. And that ID is broadcast continuously over the course of a day. So if you actually have a look then, if you filter out all of the sort of boring traffic stuff, like congestion, then you get interesting things coming out. So I modified it so it prints out the encryption ID, and then you get these temperature reports. And I thought, oh, you know, interesting temperature reports. Maybe I can create pretty graphs of how temperature changes through the course of a day somewhere in the Bay Area. But as it turned out, I kept looking over the course of each day, and I noticed these patterns appear. So every day there would always be 3 unique temperature reports. And it turned out that it's not actually really temperature. So when I say temperature from now on, that's simply what the standard claims is the translation of this event ID. It's not actually a temperature report. It's weird. But what happens is you get these 3 unique lines every day, a temperature for a particular encrypted location. And once you actually start logging all this data, I would check every day and make a log for that particular key ID. You get these patterns. So you get this group of 3, and over the course, while you're in the same group period, let's call it, the encrypted location IDs would be the same, and the temperatures would be different. But you can see these patterns form with the groupings. So what we want to do is then find out the hidden value of these location codes, which is the plain text location code that's been encrypted, and also this is the unobserved value, and maybe recover the key. So we would collect this data, and then you can build up this table over time. So imagine days going across the top. We have our key ID, which translates to some hidden key, and then we have these periods that can randomly change. They can persist for several days or weeks and then just change. But the idea is that you build this table that maps from your unknown key to your unknown plain text location to the event that was transmitted and the encrypted location. And so you build this table up. And then once you have sufficient amount of data, then you can do some analysis, and 16 bits is obviously very short. You have this reuse of these and patterns through these groups, and you can use singular events that occur as well to help with your breakdown of this data. And these singular events you can then sort of use as known plaintext. So singular events are unique occurrences, such as this odd one where there was some object reported to be on the road. This doesn't happen very often compared to, say, traffic congestion, which is everywhere. So once you've done that, then you build this sort of table, and then you start iterating and doing this exhaustive search. So the first thing you do is you calculate every possible key and every possible plaintext location that can match the results that you got for key number 1 and this potential hidden location number 1. And then you start filtering. So you repeat for that same day with that same key ID for the other 2 hidden locations. And then you take out all the possible keys that don't work, because you verify. You take the possible key, you take the encrypted location, you take the possible unencrypted ones, you put them through the encryption process and see whether they match with what you got. And if they don't, and you tried all the possibilities, then you take it out of your pool. And so you iterate then on all of the other keys, on all of the other locations. Another way of looking at that is you have your incoming data, you have this iteration loop, you have your pool of possible locations, pool of possible keys, you keep going through validating, refining, removing the invalid entries, and then at the end you're left with this. I haven't collected all the data, but it's looking pretty good so far. Some encryption IDs have 1 possible key match. And the interesting thing is, due to the algorithm, you can have multiple possible key matches for any one day, but because of the nature of the algorithm, you can query an encrypted location code and get one unencrypted match back. So that's how that works. And then, unfortunately, these singular events are usually these terrible things, this is reported on the air, so vehicle fires, flooding, hopefully everyone's okay. But unfortunately, this makes for a good additional input point, data sample for the system. Okay, so that's RDS. Aviation radar. You might have heard me talk about this before in the context of MODES and ADS-B. Just a quick recap then. Primary surveillance radar is when you've got the big dish that spins. And secondary surveillance radar is this antenna across the top. The primary system works in a way that it sends out this big radio pulse, and that is then reflected off the metallic skins of aircraft and anything else that happens to be a good reflector for RF. It's collected in this big dish, and then they paint this radar scope that spins around. You've seen it in the movies and photos and so on. The secondary system is different in that this sends out an interrogation, and that's received by the transponder that needs to be on an aircraft. The transponder hears the interrogation and then sends back to this antenna the squawk code or the altitude of the aircraft, so that air traffic control can plot it. Instead of just having these anonymous blips that come up, they can label it on their radar scope. So this system is an active system. You need the transponder on the aircraft. The primary system is a passive system. You don't need to have a transponder active or anything like that. The object just needs to be there and have a sufficient radar cross-section so that it can transmit some sort of RF energy back into the receiver. So with primary surveillance, the radar continually sends out what's called a bang or a strong pulse, and then it waits a little while in receive mode for any echoes that come back off objects, and then it starts again. This is called a pulse repetition period or pulse repetition frequency. And with ADS-B, which is part of the active system, these transponders continually and independently send out position, heading, altitude, vertical rate, flight ID, squawk code. And the typical 747 has 31 radios, which makes somebody like me really excited. But anyway, next time you fly, which is probably quite soon, you can try spotting all the different antennas that are both above and below the aircraft. So this is what a MODES frame looks like. You have this preamble at the beginning, a certain number of pulses positioned appropriately, and then, interestingly, remember from Manchester encoding, this is exactly the same sort of encoding here. So depending on which bit is actually on, then you get your bits out and you can form a packet. Now, you may have heard me talk about this before, and others as well, so I'll skip all the details, but this is what a GNU radio, this is my GNU radio decoder that I wrote many years ago, and you can see the packets coming in there. You've got the preamble up front, and then your payload after that. You may have seen these, but I'll show them again. You can do pretty plots. So this is a system I put together called Aviation Mapper. These are all the planes flying through the Bay Area. You've got SFO, SJC, and Oakland International Airport. When transponders go bad, they produce all these crazy graphics on your screen. Basically, the position reports are flipped the wrong way around. So you get what I call these sort of colored rainbows. You can produce really nice flight trials to see where the air traffic is going. This is San Francisco International Airport. I went there with my B200 at the edge of the runway there. And it's cool because you can kind of track planes as they come in. This is a parallel approach. You see these two icons, they're both green. There are the planes coming in. As soon as the nose wheel will touch the tarmac, you see that one already did there in the top. It went red. That one's going to go red in a second when the nose wheel comes down. There you go. And then they taxi back to the terminal. You can also do this for takeoffs. I think this is a Virgin America flight here about to take off on this runway. I've sped it up a little bit, obviously, but it kind of looks cool. As it does, that'll go from red to green then when it's rotated and lifted off into the air. There it goes. Up, up, and away. It's just incredible when you look at the speeds to which they accelerate and then suddenly take off. I love aviation. I think it's one of mankind's coolest achievements. Anyway, there it goes. It's following the flight path that another plane just took off prior to that. And look out for the plane in the top right. Oh no. But it's okay because they're at wildly different altitudes, as you can see. Now, since altitude information is sent as well, you can plot this in real time in Google Earth. This is the sort of 3D front end that I created for it. That's that same plane taking off, and you can see one in the distance coming in to land at Oakland International Airport. There's SFO and other planes sort of taxiing about. Off it goes. There's that same plane coming across overhead. And why not do a virtual cockpit view so you can be in the pilot seat and experience what the takeoff is like yourself. So this is that same plane from that point of view. And this side I have running live for Sydney. I moved from Sydney, Australia, and the night before I got on the plane to move here, I was in some tower in one of the suburbs setting up my USRP 1 that's been running ever since there. So you can go on my website and actually look at the live 3D airspace of Sydney using this system. This is actually coming back from the west coast, sorry, the east coast, landing at SFO. This is sped up again a little bit. And coming in for landing there, boom. And then waiting for the holding point. And then Google Earth did something really weird with their extrusion of the automatic extrusion of the burnt out fuselages of planes, it looks like, at the airport. I don't know what was happening there. And in addition, so this is Sydney now. Apart from Mode S, aircraft also send ACARS messages, which are like text messages, and these are shown up in these balloons. These are messages like automated status reports from the engines back to Rolls-Royce, or it might be, there's a bad transponder again, or it might be flight path information, which is these thicker white lines, or information back to air traffic control and various other status messages. Now, I found that there were a lot of messages regarding blocked toilets on aircraft, so I've added this Easter egg for that. And you get flight information like these. These are the flight plans for aircraft that are going into Asia and across to Western Australia. Now, so that's all the active system. Remember, this is where the aircraft is transmitting this information down to the ground that you can receive. What about the primary system? This is the passive system where you have the big radar spinning, sending out a big pulse. What about that? So, as it turns out, in the Bay Area, near Moffett Air Force Base, there is this ASR-9 primary surveillance radar. This is pretty much the main radar that's used in all airports across the country. It spins around, there's a picture, and I went out there with my B200, there it is in the background, and as it spins, just look at the left-hand scope there, it's being triggered by the big pulse that comes out of the radar, and can you hear that? Not the noise from my laptop. Yeah, did you hear that? So that's actually the audio that I filtered out as it spins past the radio. So you can kind of hear the crackling, which is all the pulses going out. And initially I wanted to look at this because I wanted to derive what the parameters of the radar actually were, like what the pulse repetition frequency was and the rotation rate and so on. But as I was doing that, I noticed, let me just play it again. You can see here, this big bang is the big pulse that comes out. But just after that, you see that there are these other little pulses that appear. Just if you can see there's some other stuff that happens. And I thought, well, hang on a minute. Could that be radar returns? They're probably going to be close in from ground clutter and buildings and so on. But there's clearly stuff coming back. And I thought, well, maybe you can plot that. Now, just remember, for this entire bit, all I'm using is this little radio and that omnidirectional whip antenna. I'm not using a directional antenna with lots of gain like that. That's the next step of the project. But what you actually see then are these radar returns. So remember this diagram, if we actually pull up the time series plot of the magnitude of the data that I recorded, you can see on the left-hand side here the big bang there, and then these returns that come back. So what you can do is, if you ever are in the Bay Area and you want to hang out with me on a big hill next to a water treatment facility near the radar, then it's quite a nice view actually at sunset. But some of my friends and I went up there last Friday to try and collect a little bit more data. You see we've got the antennas out, and they were really nice in terms of sacrificing their hand, because unfortunately the Thunderbolt connector on my laptop died, and the only way to make it work is if you push the Thunderbolt plug-in with all of your might. And that was actually hooked up to a PCI Express adapter box, which had a 10 gigabit Ethernet card in there that was then hooked up to an X300, X310, so we could sample at 100 megs a second. And it's all powered off a battery there, so it was a bit of fun. This was a very nice reminder of the good times I had with my friend Matt Robert, who actually got me into SDR back in Australia. This is the same kind of scene, but instead on the hill overlooking Sydney Airport. So good times. I highly recommend you do it. Grab some batteries, laptops, SDR, go to some location, and the police come out. But anyway, so once you record all those returns from the radar, you need to do some processing. So the first thing you do is you do an average, windowed average over your entire sample stream to figure out what the distribution of magnitudes are. Because the vast majority of samples you receive are going to be noise. And that's this big peak here on the left-hand side. This is a histogram, so your magnitudes go along the bottom and your counts go up. Now, if you do a log scaling of this, you can see that this is mostly noise, and then you've probably got some interesting stuff here on the left-hand side because you're not going to have your pulses come back too often relative to all the other samples. So you pick some threshold here to say everything below that's going to be noise, I'm going to ignore it. Once you do that, then you look at the left-hand side of the previous graph and you think, well, these are probably going to be returns, and what we want to do first is we want to synchronize to the strongest pulses which come from the radar. So they're probably going to be few and far between, so again we're going to pick some high threshold here, and that's going to be our synchronization level. So you do the log scaling and you probably pick something around about there. Once you do that, then you can do a histogram of the length of these strong pulses. You can see there's quite a big peak there. So the chances are that our sort of standard pulse length is going to be, whatever that peak maps to down the bottom, and you program that into the system as well. Once you do that, then it'll actually detect the strong pulses, synchronize, and then you can produce this overlaid plot. So this is lots and lots of strong pulses overlaid on one another, and you can use this to check that in fact the system is working. You have this nice empty space in the middle. If you've seen eye diagrams, this is kind of the same thing. After that initial pulse comes out, then you have those interesting returns after that. You load more on, looks good, do a log plot, and some more interesting things come out there. Now, remember how I was talking about pulse repetition frequency? This is the period from when a pulse is sent out to when the next pulse is sent out. This here is showing you the number of samples between one pulse and the next pulse. Now, the odd thing here is that you actually end up having these two lines coming out from all these, the grouping of these red dots. I was expecting one. And what this actually shows you is that the radar is operating in this mode called dual PRF. So it's actually switching between two pulse repetition frequencies. It might send out like 10 pulses at one, switch to the other one, and send another like 9 or 10. It's completely random, and it keeps switching back and forth. And it does this to resolve ambiguities. So the system needs to take this into account now as well. You can program that in. Once you do, then you can draw this histogram of the PRFs, and you can see very clearly you have a PRF of, this is about 950 hertz, and the other one is 1250. So these are the two PRFs that's switching in between. Program that in. Once you graph the amplitude of the strong pulses, this was, what is it, six revolutions of the radar, so you can see the peaks when it sort of begins to face the radio. And this is sort of zooming in on one. Once you actually program in everything and then it starts tracking all the pulses, not just the strong ones, then you get everything in between. So these are when it sort of faces the radio, and this is everything outside that as it spins around. Now, once you actually synchronize, this is what it looks like if you animate it. So the first pulse here is what came out of the radar, and everything after that is what is actually coming back from that main pulse back into the radio. So this is close in. As I said, it's not going to be like an aeroplane. It's probably going to be big buildings and so on. Now, you can turn this into a pretty plot. This is what it looks like. So the way this works is that every scan line going from left to right is triggered by a pulse that comes out of the radar. And then once it's triggered, it just starts recording for this amount of time until it reaches the end of the scan line. So this is pulses going down the vertical, and across the horizontal, it's just time. And you can see these interesting patterns start to emerge. If you zoom further in, you can see this kind of odd shape here, and various other things pop out. And then, so you got that, and then you got this odd hotspot out further out. If you do an polar unwrap and put it on Google Maps, you can see that it perfectly aligns with physical features in the Bay Area. So let's zoom in a little bit. The radar's here. Then you've got all this sort of ground clutter and buildings and so on around the shore. And you've got this odd kind of stippled line that's enclosed in red. And I was thinking, what could that possibly be? I mean, that's on the water. It doesn't seem to match anything that I've seen. As it turns out, it's all the power line pylons that cross the bay. So they're actually reflecting the radar energy that comes off the primary radar. Now, if you look further out, those other hotspots actually map to the bridge, and I think there's some sort of a gasoline pipeline or something like that, and San Mateo Bridge further out. Now, that was one revolution. If you do all 6, then you can see this kind of repeats over and over again. But what happens when you actually overlay all of these images on top of one another? Well, what I've done here is I've taken the very first revolution, mapped that into the red channel, taken, I think, the 4th one, mapped that into the green channel, and taken the very last one and mapped that into the red channel. So what happens is all of these static objects that reflect the radar energy will then come out in white on this plot, and anything that ends up moving, you'll see this kind of RGB triplet or RGB smearing, because essentially your colors map to time. So there's nothing interesting in this one, it's all white. But look at this one. See that? Something was moving. So we can zoom in on that, there's some sort of RGB smearing there, and this is another plot, same thing, something's moving further out. Now, as I said, bigger antenna, more gain, more directional. You can look at objects that are further out with smaller radar cross-sections. I don't actually know what this was, but if you do a polar unwrap, you can see that it's up there. And if you put the map underneath, then it's on the shoreline. You can't quite see it, but there's actually a road here. And if you consider the rotation rate and the distance across which it traveled and so on, I think it was probably a truck. It might have been a truck moving about 40 kilometers an hour. That's just my initial guess. And this was actually from my hotel room just the other night when I got in at Vegas. You can see a BA 747 landing. I just had the system running there. The problem with this setup, though, was that the primary surveillance radar for Las Vegas McCarran Airport is here, Mandalay Bay is there, and it's essentially a straight shot over. So anything in this larger region, you won't actually be able to resolve. And if you think about why, when the radar spins and turns and points in my direction there, it's going to not only saturate the receiver because it's so powerful, but if there's some other object around here, you're receiving samples and you need to consider the flight time of your wave, of your photons. So you consider the main pulse coming out, it's going to go off something here, come back together, and it's just going to be hidden underneath all of the main energy. So when you want to track objects in this kind of separated biostatic setup, they have to be further out. And you can actually take this into account in the system. So you can generate what's known as a spatial distortion map. Now, if the radar and the receiver are at the same point, the transmitter and the receiver, then what you want to look at is this 2D offset. The red channel is the spatial X offset, and the blue channel is the spatial Y offset for this spatial map represented by this area. So there's going to be no spatial offset because they're co-located. If they're not, if there's some biostatic setup where your transmitter and receiver are separated, then you can barely see it here, but there's sort of this differing shading of blue and red. I don't know if you can see that. So the radar is sort of moved off a little bit at a particular angle from the receiver. If you exaggerate this and normalize it to the area, then you can very clearly see this sort of spatial distortion that you have to apply to the data that comes back to make it look like in your plot, original plot, that your receiver is actually where your radar transmitter is. But anyway, that's future work. So this is a plot from the Mandalay Bay. There's not a lot going on there, but if you... no, this one there is. So there's some sort of smearing there. It's very weak. Again, remember, this is just an omnidirectional antenna like that. And there's another one. This was quite odd because this is quite close in, some clutter, but it only appeared in one of the rotations. So I'm not entirely sure what was going on there, but we can analyze it some more later. So that's primary radar. On to the next thing, RFID. You're probably familiar with Fast Track or Easy Pass. They're toll tags that you put on your car. They're read by the bridges when you go through, and then you're charged for your use of the road there. It uses 900 megahertz ISM. There's a wake-up signal to wake it up, and it's pulse position modulated payload like Mode S. And it uses backscatter modulation so that the receiver actually receives this backscatter energy. And so what's going on there is that your tag doesn't have an active transmitter in it. It's just a little long-life battery, but there's an antenna inside it, and it has a radio receiver. So when it's woken up and it receives this payload, it will actually change the impedance across the antenna in such a way that the receiver can see those very subtle changes in radio energy coming back, because the antenna will change its characteristics, change its radar cross-section, and the receiver can actually pick that up. There's this great talk at Black Hat a few years ago, and this was quite inspiring for me. But my initial questioning came from when I saw these antennas in San Francisco. I was wondering what they were used for. So I got the B200 out and had the Yagi pointed at it, and I recorded this thing and had a closer look. And then I went to the toll gates at the Golden Gate Bridge and looked totally inconspicuous and not suspicious, sitting there in the bus stop with my antenna pointed at the toll booths. And I saw the same signal. So if you look at that, this is what's being transmitted out. You have your wake up, you have some sort of preamble there, you have your pulse position payload, and then you have this constant carrier that's used to energize the tag, and then the backscatter will be modulated on top of this, because when you receive this, the signal will have these subtle variations in it, and you'll see what that looks like. So this is just zooming in. You can see the payload there. It looks very much like a MODES frame, and then you have this constant carrier. So I'll skip this, but essentially it shows you how I can use what's known as an RF circulator to turn a single antenna into a simultaneous transmitter and receiver. Essentially the RF energy comes in, goes out of the antenna, but it blocks any of that energy passing through to the receiver, and then anything coming back from the antenna goes into the receiver but doesn't go around any further. It's a really neat device. And this is the GNU radio program. This is being transmitted out, and you might recognize this from the plots before. This is what's actually being received. So you receive a bit of the signal that you sent out, but what you want to look for is this area here. So imagine this is just a carrier. Don't worry about the squiggles there. But the interrogation goes out when you put a tag there. Then you see you've got some modulation on top of that, and that's actually the backscatter from the tag. And that's what it looks like, sort of blown up here. So this is additional modulation on top that you can then decode. And that contains your unencrypted, unauthenticated tag ID that identifies you as an individual. So this is the preamble it's looking for in that backscatter modulation. There's a fixed series of bits, and when it hits the preamble, it knows that a packet is then coming and will decode that. So as you can see here, you have, remember, like with the frequency shift keying from the pager, you have exactly the same scenario here. So it decodes anything above and below into a 0 or a 1, and that's how you determine the tag ID. So this is a little video here to give you a better idea. This is what's going out, and this is what's being received, and you can see here is that backscatter modulation when I'm actually holding the tag over the antenna. And you can see that it's moving there. So there's nothing there now. There's nothing there now, it's just supposed to be a carrier, and now I put the tag back and you can see that it's being modulated there. So backscatter is really cool, and it's used in all sorts of different areas. So here I was just reading this tag outside. I've just put one under the windshield there, and I can put the antenna over there, and then it picks it up. This is the flow graph. This is both transmitting and receiving out of the same unit through that circulator, and that's just the fast track decoder block there. Another thing we tried to look at is the keyless entry for example, the Toyota Prius. We've got that wire there stuck in the handle, which is where the low frequency broadcast comes from the car that wakes up the little UHF remote control. And the UHF portion we're receiving on that little whip antenna there. Here we're actually using the X310 because we're doing AHF or LF recording with one side of the one channel, and then VHF, UHF on the other side. And then my colleague here is just pressing the button on the remote sometimes, so we get some additional activity. And this is neat. This is the time domain of the LF portion. So this is the car constantly sending out things. Is anybody there? You know, is my real owner there? Again, you can see the pulses. You can decode that. Zooming in there, you can, pretty obvious that you can turn that into zeros and ones. This is actually the reply, so the car sends out a challenge, and this is the reply from the UHF remote. And again, you can see this on and off keying here, and you can turn that into zeros and ones. I'm pretty sure the crypto is secure, so I didn't go beyond this, but just to give you an idea that with these sort of systems that use different frequencies simultaneously, you can do this analysis. Now, this is using baud lines, so I've actually got both FFTs overlaid on each other, so you can look at them as they happen together in time, which is really handy. The blue is the low frequency coming from the car, the red is what's coming back from the remote. And so if you look at that, in time you can see that the broadcasts come periodically from the car, and then every so often the remote answers with this challenge, which is what you see in red. And this is a little plug in a little block that I made for GNU Radio. This is the original flow graph running here, but you can just drop this block in, have baud line come up and visualize things there. And yeah, that's just the block there. The final thing with RFID was I just had a quick look at using the badge system in our building. This uses essentially backscatter as well. You have the chip in the card, and then every so often the reader will send out this broadcast, this interrogation, which is this periodic thing here, and then below you see that the card then replies. It has a chip in there, it has an antenna that changes the characteristics of, and it'll read out the data there. So that's what's happening here. You can see as you zoom in, the stronger ones are what's coming from the reader, and the weaker ones are the backscatter from the card, and then you can go ahead and demodulate that. I imagine that's pretty secure as well. That's just zoomed in some more, as you can see there. All right, so just to wrap up then, who's heard about the ISE3 project? Google actually followed our activities and they launched their website. What is it? Space. I've had a mental blank. I haven't even seen it yet. It was just launched yesterday. It's like Space Probe for All or something like that. So I encourage you to check it out. Where is it? I don't know. Just have a Google. It's pretty cool. So NASA sent out the space probe over 36 years ago. It had a lot of firsts. So it was 1978 that it got sent out, and it tracked a comet for the first time, studied the solar wind and the Earth's magnetic field, and they found that it was coming back toward Earth because it has this interesting orbit that sort of goes ahead of the Earth and goes around the sun. And they picked its signal up because the radios were left on. And so they found that it was coming back toward the Earth, and they thought, oh, cool, well, let's see whether we can try and talk to the satellite, talk to the space probe, and maybe fire its thrusters to bring it back into orbit around the Earth, and then turn the science instruments back on and open it up for STEM education for public consumption. And so they did a Kickstarter and raised some money. And then the problem was that NASA actually had gotten rid of all of the equipment they used to talk to the space probe from their deep space network ground stations. So they realized, well, hang on, we need something as a replacement, and therefore they saw SDR was a potential, and they got in touch, and I came on board. And so we went to Arecibo, which is the world's largest sort of single-dish radio telescope in Puerto Rico. And you can see the platform here, which is suspended above the dish. This is called the dome. That houses the actual receiver and transmitter equipment. And then the raw RF is then piped back down to the control room. So this is kind of the view from above there. The scale is just mind-blowingly incredible. I mean, this thing is absolutely huge. I went for a jog once around the dish, and it's like 1 kilometer in circumference. It's insane. They also have they have two 1 megawatt klystrons that they use for S-band radar imaging, and when you actually multiply that by the gain of the dish, it comes out to 2 terawatts, which is insane. Birds sometimes fly in there and they get zapped and die and then boil and burn. So once we actually hooked all the stuff up, here we used the N210, the USRP N210, which is a network device, hooked that up to the IF patch panel. We actually saw the weak carrier being broadcast by the probe. And the reason why it was weak was because the ephemeris, which says, basically we need to point the dish in the sky, was old. And once, the gurus there did a bit of pointing on the dish to peak up the signal, it was really, really strong. This is the weak version. You can just see it there. It's slanted due to the Doppler effect as the Earth rotates. But this is the GNU radio side of things, and you can see the signal is really, really strong. So then the next challenge was to send a command to it to turn telemetry back on after all this time so we could see and assess the state of the space probe. And as we were sending things out, I was just using a B200 here to verify that, in fact, the RF energy was leaving the dish. It was a good little test. And then this is what happened. So that was the moment where we actually saw that unmodulated carrier suddenly turn into modulated data, and the telemetry had been turned back on that transponder. So that was a great milestone in the project. And then after that, we were recording telemetry on both channels. That's transponder A and transponder B. The signal was very strong because, of course, you're using the biggest dish on the planet. And then since then we've processed that a lot. The next stage of the project was to actually fire the thrusters. So this is some software that I put together. You can download this off my GitHub and connect it to the live stream on my website. That actually shows you some of the telemetry elements. This is all the stuff about the propulsion system on the space probe. And we would look at this when we would go and then program the thruster firing on the space probe. So we wanted to fire this thruster this number of times to change its trajectory. And then we also created this graphing system so that we can actually look at what was happening. This is the signal strength as reported by the space probe. And as we would fire the thrusters, this is the accelerometer data that comes back. So every time you fire the thruster, the accelerometer should register a pulse to let you know that it worked. And so I know we're running short of time, so I'll wrap up. But the problem was that there's plenty of fuel left on the space probe, but you need pressure to push the fuel out through the thrusters, and that's nitrogen, and unfortunately that nitrogen seems to have disappeared over the 3 decades. So we tried every single combination, but we just couldn't get enough thrust out. So it's going to continue on its merry way. It's going to do a lunar flyby today or tomorrow. But we've turned the science instrumentation back on, and we're receiving science data from it. So that's good. This is the team outside McMoon's, which is the old McDonald's that was converted into mission control at NASA Ames. Thank you very much. Okay. Sorry, I completely forgot to mention, if you have an SDR here and you want to tune to 915 megahertz at 1 megasample per second, I've been transmitting something the entire presentation. It's this little thing I've been working on. I'll leave it running while this is the last thing I'll disconnect, or I'll take it over there. But if you want to tune in 915 megahertz, 1 megasamples per second, I haven't updated it from last year when we were at a different conference, so excuse the plug, but you might enjoy it anyway. All right, cheers, thanks.